Good afternoon. My name is John Weese. I'm a professor of mechanical engineering at Texas A&M University. My objective this afternoon is to give you information about the mathematics part of the fundamentals of engineering examination. I'm going to do this in several parts. The first part will be to review the information that is contained in the reference handbook, which you will be allowed to take to the examination with you. It is especially important for you to understand what's in that booklet, because only those aspects of mathematics contained in the booklet should appear on the fundamentals of engineering examination. Consequently, there may be some aspects of mathematics that you're worried about that actually won't appear on the exam because they're not in this book. On the other hand, there are probably lots of things in here that you can profit by studying and reviewing prior to the time you get to the exam. I'm going to go through this page by page, and you may find it useful to go through your manual while you're watching what I do. Starting on page 3 of the manual is a copy of the starting material on mathematics. It begins with the most elementary types of information so that you start off with things that are very familiar, such as the equation for a straight line. Now, a straight line, as shown in the figure here in the first equation, generally has the form of a constant times x plus a constant times y plus a third constant equals 0. And that will give you the equation of a line in an xy coordinate system. The more familiar form that you learned in calculus is the form y equals mx plus b, which is the second line shown in this page. Now, the m value is the slope of the line. It's the ratio of the rise to the tread. So consequently, that's a familiar term. Mx and b is the y-intercept. That's where the line crosses the y-axis. In this manual, you will find a couple of other forms of the equation that will allow you to compute the slope if you are given other information, and it will also allow you to calculate a very important feature, which is namely the slope of an orthogonal line. It's very common in these examinations for someone to give you a problem and say, write the equation of a line perpendicular to something. When you have to write it perpendicular to something, if you know the slope, then you take the negative reciprocal. You will notice right here, for example, they point out that m1 is equal to a minus 1 over m2. And that gives you the relationship that is very useful for many kinds of problems. It points out that two lines are perpendicular if m1 is equal to the negative reciprocal of the other one. It also gives you other formulas like the distance between 2 points, which are relatively obvious. In your high school, you learned about quadratic equations. Equations of the form ax squared plus bx plus c equals 0. And almost everybody can recite the equation that the roots are equal to minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. But in case you're having a lapse of memory, it includes the formula for you here. Many of these fundamental of engineering examinations include questions related to conic sections. Now, conic sections, the simplest one is the circle, but another one is a parabola, a third one is an ellipse, and a fourth type is a hyperbola. These curves are all generated by intersecting cones, such as shown in the figure in the manual. The various shapes come about from intersections with those cones through planes at various angles. The parabola, which in some respects is the easiest one to deal with, is shown in this part of the figure right here. The general form of a parabola is shown, and the parabola in this particular case opens out along the x-axis. There is a focus for a parabola, which is shown right here, and the other features of putting the parabolic equation together are shown. You'll notice that the terms involving y are squared in this case, and x is the linear terms. The center of the parabola is at hk in the form shown here. There is a standard form of the parabolic equation, which is the one listed, and it gives you various kinds of information. There is a property called a directrix for a parabola, which is a very interesting sort of thing, but interesting mathematical features are probably not what you have in mind when you're getting ready to pass the fundamentals of engineering examination, so I will resist the professorial temptation to digress about the wonders of a directrix. The next form that they show in the manual is the case of an ellipse. An ellipse is a closed figure as contrasted with a parabola, which is not. The general form of an ellipse has y minus h quantity squared divided by a squared. It's x minus h quantity squared divided by a squared. I'm reading it a little farther away than I thought. Plus y minus k quantity squared divided by b squared equals 1. That's the standard form for the equation for an ellipse. And it gives you relationships for the eccentricity of an ellipse, which is a measure of how flattened compared to its length an ellipse will be. And this is the equation for the eccentricity. An ellipse has two foci, and it tells you the location of those two foci. A hyperbola is an open curve, and the hyperbola parts are shown here on the left and the other one on the right. The general form of the hyperbola at first looks a little bit like the general form for the ellipse, but there is an all-important difference in this algebraic sign between the two terms, because you will notice there is a minus sign between the first term, x minus h quantity squared divided by a squared, and the y minus k quantity squared divided by b squared. That minus sign makes all the difference in the world and opens this particular hyperbola up along the minus x-axis and the plus x-axis. These two terms equal 1 on the right-hand side of the equation. There is an eccentricity associated with hyperbolas, just like there is with ellipses, and it is given by this equation, as well as the location of the foci for the hyperbola. The most commonly encountered form of a conic section is the circle, and the equation for the circle is shown here. X minus h quantity squared plus y minus k quantity squared is equal to r squared, where r is the radius of the circle. And this general form of the equation of a circle is found throughout mathematics. The figure showing where that particular circle is located is on the next page, which is 4 of your manual, and you'll notice that the center of the circle is at the point HK. And the equation, of course, gives you the equation of any point on the periphery of that circle. There are a number of other things that the manual points out. For example, if you are drawing a tangent to the circle from some point outside, it gives you the equations for how that tangent is to be calculated. Many times you run into equations that are second order, but you cannot tell immediately from looking at them whether they are a hyperbola, a parabola, a circle, or an ellipse. But there are some characteristics that allow you to determine that. The general form for a second order equation is ax squared plus 2b times xy. Notice that's a second order term, the product of x and y, plus c times y squared, plus then a set of linear terms, 2dx and so forth. The business about whether it's going to be an ellipse, a parabola, a hyperbola, or whatever is determined by a discriminant. This one is just a little bit different from the discriminant for the quadratic equation, which you will remember is b squared minus 4ac. This one is b squared minus ac, and that difference comes through that constant 2. So you want to be watchful of that. The conditions are fairly easy to understand. If b squared minus ac is less than 0, that is negative, it's an ellipse. If b squared minus 4ac is greater than 0, it's a hyperbola. If b squared minus ac is 0, it's a conic. It's a parabola, excuse me. It is a conic in any case. If a equals c equal b, if a equals c and b is equal to 0, it's a circle. And finally, if a equals b equals c equals 0, it's a straight line. Now, there are some other features here. They show you a little simpler form of this particular equation where they have reduced some of the coefficients to 1, and it makes it a little bit easier for you to manipulate it. But knowing that that section is located in here will help you. There is only one surface given for a solid, namely a sphere. And you will find the equation for a sphere given at this point right here, namely x minus h squared plus y minus k quantity squared plus z minus m quantity squared equals r squared. That gives you a sphere of radius r whose center is located at the point x equals h, y equals k, and m equals z. Let us now move to the area of logarithms. Most of the logarithms that you will encounter in the Fundamentals of Engineering exam you will use incidentally as a part of solving problems. And your calculator will generally direct you to use those things with respect to base E. However, this document does give you some additional information. If you have to work at a base other than E or 10, and most of our calculators are set only to work for base E and base 10, the formulas are given so that you can work with other bases. But you may want to look at this to make sure that you understand how that works. Most of the things you'll encounter with respect to logarithms will be rather straightforward. There's lots of trigonometry on these exams. It starts off very simply with a right triangle. It has an angle theta. The right angle is over here between the vertical side y and the horizontal side x, and the hypotenuse r. The Pythagorean theorem is alive and well, so that x squared plus y squared is equal to r squared. The sine of theta is defined for you as the opposite side divided by the hypotenuse, y divided by r. The cosine of theta is the adjacent side, x, divided by r. Similarly, the tangent of theta is y divided by x. That defines 3 of the 6 trigonometric functions. There is, for example, a cosecant CSC, which is the hypotenuse divided by the opposite side. There is also a secant, which is the hypotenuse divided by the adjacent side. And finally, a cotangent, which is the adjacent side divided by the opposite side. Obviously, the cosecant is the reciprocal of the sine, the secant is the reciprocal of the cosine, and the cotangent is the reciprocal of the tangent. Those trigonometric functions are universal, the nomenclature is universal, and they should be relatively familiar to you. You will solve, in all probability, problems that involve the use of trigonometry. A number of these often involve the use of the law of sines. And the law of sines reads as follows. You look at the angles in the vertices of the triangle, in this case capital A, capital B, and capital C. And the opposite sides are labeled with the lowercase letters A, B, and C. The law of sines says that the opposite side divided by its sine is equal to any other opposite side divided by its sine. So A divided by the sine of capital A is equal to B divided by the sine of capital B, which is also equal to C divided by the sine of capital C. Recognize that in this thing there are three equations. The sine of A over A divided by the sine of A is equal to B divided by the sine of B, but it's also equal to C divided by the sine of C. So that's two equations. And then finally there is the third one that says that B divided by the sine of B is equal to C divided by the sine of C. Now, that's the law of sines. It's a very powerful way to address a number of problems. There is also a generalization of the Pythagorean theorem known as the law of cosines, and I will quote just one of the lines here. C squared is equal to A squared plus B squared minus 2AB cosine C. Let's see what that says. This side squared is equal to the other two sides, each squared, A squared plus B squared, minus twice their product, 2AB, times the cosine of the angle between them. That's this one. And you'll notice there are similar statements for getting the sides A and the side B. This manual has a lot of trigonometric identities. Some of them are relatively obvious. Some of them are particularly useful. The sine of alpha plus beta, the cosine of alpha plus beta, the double angle formula relating the sine of 2 alpha to 2 times sine alpha cosine alpha crops up quite frequently, as does the cosine of 2 alpha. The rest of them, frankly, are special cases of the first few and tend to be ones that are used less frequently. But it still is very nice to know that they are there in the event that you need to look up something. And you will notice as we look at the top of page 5 that there is quite a number of additional trigonometric identity formulas. After the trigonometric identities comes the complex number business. Now you probably remember that there's a complex number called the square root of minus 1. That simply is a solution of the equation x squared equals minus 1. And by convention, we define that thing as the imaginary number I, there being no real number which when multiplied by itself will give minus 1. Complex numbers have the form of a real part plus an imaginary part, such as an A plus an IB, where A and B are both real numbers. The manual shows you how to add complex numbers together, how to subtract them, and how to multiply them. Those are all fairly straightforward sorts of things, but you do have to remember when you multiply two complex numbers together that you're going to end up with a term that is an I times an I, and an I squared is a minus 1. And that's what gives rise to this minus sign with B times D when you multiply these things out. It shows you also how to divide one complex number by another. And you will notice the step over here shows that you start with A plus IB divided by C plus ID. And the first thing you do is to multiply top and bottom by the complex conjugate, which is the number C plus ID with its algebraic sign ahead of the imaginary part changed to C minus ID. And it gives the result as shown over here. Polar coordinates are used a lot in engineering work, so they are also included on the Fundamentals of Engineering examination. The polar coordinate system is defined by x equals r cosine theta, y equals r sine theta, and that results in theta itself being the arctangent of y divided by x. Now, polar coordinate systems are very common. They are not particularly difficult to deal with, but knowing these definitions are here and the fact that you can refer to them readily gives you a good reference to have at your fingertips. You will notice in this that they use a term cosine theta plus an I sine theta. There is a famous formula known as Euler's formula. If you're curious, Euler was a Swiss mathematician. Consequently, it has the German pronunciation. And the Euler's formula that is usually attributed to his name is e to the I theta is the cosine of theta plus I times the sine of theta. E to the minus I theta is cosine theta minus I sine theta, and you can get relationships between the cosine of theta and the exponentials, as well as the sine of theta and the exponentials by using the properties of these two. The fundamental one to remember is Euler's formula right here. Sometimes it's necessary to take the roots of complex numbers, and this manual gives you the techniques for doing that. I won't demonstrate it in the material here, but those of you that have the right kinds of calculators might read your manuals so that you know how to take, for example, a square root or a cube root of a complex number. Calculators that are more fancy than the one I have with me this afternoon are capable of doing this, and those calculators are also set up in such ways that you can add, subtract, multiply, and divide complex numbers. The manual includes information about matrices. It includes information about the multiplication of matrices, the addition of matrices, the identity matrix, the transpose, the inverse, and so forth. They write this out in terms that may look a little bit daunting. For example, they describe a matrix A in terms of its elements and another matrix B in terms of its elements. And then they describe a matrix C and how it is multiplied. You may look at that definition over there and think, good heavens, someone is about to give me something that I don't care a whole lot about. But let me take just a minute and show you a simple multiplication of two matrices. Let me start off with a matrix, for example, that is just a 2 by 2. Let me take the numbers 2, 3, and 5, and 6. And I will take with this just a very simple little matrix, which is a column. And I'll make it let's say 7 and 8. I'm making these numbers up as I go along. The way matrix multiplication works is you take a row of the matrix on the left and multiply it with the column in the matrix on the right. So the result on this thing is going to be the following. It's going to be 2 times 7 plus 3 times 8. That's the element that'll go in the top. The element that'll go in the bottom will be 5 times 7 plus 6 times 8. Now, if we can do this mathematics in our head, 2 times 7 is 14, 3 times 8 is 24, and we end up over here with a first element that is 14 plus 24, and that's going to be 38. For the bottom element, we end up with 5 times 7 is 35 right there, 6 times 8 is 48, 8 and 5 is 13, and 4 and 4 is 8, and we end up with 38 and 83. And my colleague here is nodding his head. I guess I did it right, because that was done on the spur of the moment. But I know when you read definitions like that, and if you do not engage yourself in this activity on a really regular basis, when you look at a formula like this one over here, where it's got a big sigma from I equals 1 to n, and it's L equals 1 to n, and you look at those indices over there and you think, what in the world is really going on? It's not that hard. So practice with a few of them. You will find some practice problems in various places where you can check this out. When you add matrices together, it's duck soup easy. They have to be the same size. You will never add together 2 matrices that don't have the same number of rows and columns, because that just doesn't work that way. You just add them element by element. You can start in the upper left-hand corner of the first matrix, add your element to the upper left-hand element in the second matrix, and put it in the upper left-hand element of the result. So it's easy to do. You just go ahead and march across, adding up the elements one at a time. And that's essentially what this little equation says for you here in terms that are not quite so easily understood. There is a thing called the identity matrix. Now, they go through and give you a definition for the identity matrix, but I'm just going to write down a simple one for you here so that you can see what they look like. The identity matrix, first of all, is always a square matrix. It has the same number of rows as it has columns. So when you write the identity matrix, for example, the identity matrix for a 2 by 2 is 1, 0, 0, 1. Similarly, an identity matrix for a 3 by 3 is, make it a little bigger, 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay? That's the identity matrix for a 3 by 3. There is a thing called a transpose of a matrix, which just interchanges the rows and the columns. And oftentimes a symmetric matrix, for example, it's symmetric about its main diagonal, its transpose is equal to the matrix itself. There is an inverse of a matrix, and that's kind of a special animal. And they're not easy to calculate. But basically, if we have a square matrix A, and I'll put brackets around him to make him a square matrix, there is a thing called A minus 1. It's inverse. And when you take A times his inverse, A minus 1, you get out of that the identity matrix. That's as close to division as you get in matrices. Matrix division is not defined, and it's a mathematical no-no. You will never find a question on the fundamentals of engineering exam that asks you to divide one matrix by another. I hope. All right. After it goes through matrices, it goes into determinants. And it explains a lot about determinants in the process of leading you up to the fact that the only determinants mentioned in this manual are 2x2s and 3x3s. And it shows you how to evaluate them. Now, that is a piece of good news, because if you have to evaluate a matrix that's larger than 3x3, it is a more complicated process, and it requires a lot of time. So knowing that you're only going to be dealing with determinants that are 2x2 and 3x3 is comforting. Vectors are treated in several ways, but fortunately all in the form of vector algebra. The manual has a diagram that's worth studying a bit. It shows you a system of base vectors. The little vector I points along the x-axis and has a magnitude of 1. There is a similar vector j along the y-axis and another one k along the z-axis. A general vector A, notice it's in boldface, is equal to a component ax times I, that's the component in the x direction, ay times j plus az times k. Addition of vectors is easy. If you have two vectors a and b, you just add the components of them. If you subtract them, you subtract, for example, a minus b, you just subtract the b components from a. There are two types of products associated with vectors. One of them is the dot product or the scalar product. A dot B. And it's defined as the magnitude of A times the magnitude of B times the cosine of the angle between them. It's shown diagrammatically down here. Well, I'm sorry, that's for the next one. Magnitude of A, magnitude of B, cosine of the angle between them. In terms of components, it's a sub x times b sub x, a sub y times b sub y, plus a sub z times b sub z. It's called a scalar because it is a number. It is not a vector in itself. The result of a scalar product of two vectors, or the dot product of two vectors, is a number. It is not a vector. The cross product is a vector product, defined at least in some particular ways. The cross product is the magnitude of A, and I'm going to jump up here to the top. I guess that shows all right. The magnitude of A times the magnitude of B times the unit vector n times the sine of the angle between them. Going back down here to the bottom of the first column, you'll notice the vector A, the vector B, and the angle between them, and you'll notice a vector C pointing up this way, perpendicular to that plane. And that's given direction by that little n. Notice the definition up here. They point out that the cross product can be written as a determinant. And that's the easiest way to calculate one of these things when you have to perform it. Due to its definition and the way in which this unit vector is assigned, requires some explanation. You take the vector A and you rotate it into the vector B. You take the vector A and you rotate it into the vector B. You'll notice I used my right hand and I had my thumb sticking up in the air. People who are doing vector mechanics always look like flycatchers going around the room trying to make sure that you get the direction correctly. So you take the magnitude of A and you times the magnitude of B Rotating it in that way times the sine of theta gives you the vector product. Now, due to the direction that's in here and the involvement of the right-hand rule, vector products, cross products, change sign if you reverse the order of multiplication. So A cross B is equal to minus B cross A. There are some identities for these that are given up here. For example, there is the triple scalar product, or this is the first one is the one that gives you A dotted with the sum of two vectors, B plus C, and it shows you what it is. If you take a vector A and perform the dot product with itself, it gives you the square of its magnitude. All of our little unit vectors are mutually orthogonal, that is mutually perpendicular, so they come out in this fashion. And finally, if vector A dot B is 0, then the two vectors are perpendicular. They say here that one of them is 0 or the other is 0. That's true. Sometimes we say the 0 vector is perpendicular to everything. There are also identities given for the cross product. Excuse me. And you will find the triple cross product listed out here. And once in a while you will find problems that involve some of these, and the one that's probably best to take note of is A cross parenthesis B plus C, because it is a little easier to work in that fashion. Now, the next thing they go into is progressions and series themselves. Arithmetic progressions, they do in the form where you just add a constant term to each one. The first term is A, the second term you add an amount D, and each time you go along you add D more. They're relatively easy things to deal with. If that sounds awfully confusing, for example, the first term is A, the second term is A plus D, the third term is A plus 2D, and so forth on down the line. Now, when you're adding on a term like that each time, of course, those have to be finite progressions, or they eventually diverge. They give you some formulas here for calculating the nth term and also for calculating the sum of the series, or the progression. Geometric progressions are a little more common. There may be someone watching this who has financed his house or financed his automobile, in which case geometric progressions are something you know about because they're used to calculate interest payments, among other things. The first term is A, and then there is a multiplying ratio. So if the first term is A, the second term is AR, and the third term is AR squared, and the nth term in general is AR to the n. AR to the n minus 1. AR to the n is where you make the last payment and the car is yours. At any rate, it gives you formulas for getting partial sums and so forth of these, and the conditions under which they converge. They give a lot of properties of series up here, which is useful to review. Power series are used a lot in engineering type work, but in all honesty, the problems associated with power series frequently are rather involved, and so consequently the likelihood of you running into an extensive power series problem is somewhat remote. They also give the form for Taylor's series, which is a technique that's used for writing power series for functions such as sines, cosines, and similar things of that nature. Probability and statistics has become a little more prominent in exams in recent years, and we'll see some problems in this as we go along. The first thing it tells you about is permutations and combinations. Now, Permutations are the number of different permutations of n objects taken r at a time. This is like, let's see, I want to pick up a good example. This is like a license plate. If you look at Texas license plates, of course, at least the ones that I have, are 3 letters followed by 3 numbers. The license plate is highly dependent upon order. If I think of the letters themselves, and if indeed we could have access to all 26 letters, we would have a number of ways we could form those first three letters. Obviously, we could make an AAA, or an AAB, or an ABC. And there are some other, whole bunches of other 3-letter combinations we could make. This is a way of figuring out how many of those you could do. If you had the population of 26 letters and you were taking them 3 at a time, in our example just mentioned now, you would have 26 factorial divided by n minus r, that would be 26 minus 3 would be 23 factorial, and that's a large number of combinations that you could make. But since order is important in permutations, it turns out to be a rather large number. Sometimes, however, order is not important, and it's really just the combination of articles that's important. Unless the United States military has changed since I was on active duty, you probably have some colleagues who occasionally engage in games of chance, such as poker. Yours truly is an Air Force veteran, and I know that some of my faster-moving colleagues, Lee, occasionally engaged in such activities. I don't know what branch of the service you were in. But at any rate, if you think about poker hands, and let's play a game of 5-card stud, and you're dealt a hand of 5 cards. Now, when you peek under there to see what you are dealt, you can rearrange them, at least mentally or physically if you're playing a friendly game, in any order you choose. And of course, the order in which you arrange the cards depends upon what cards you got. If you're working towards a straight, you might be inclined to order the cards according to the numbers. On the other hand, if you're working towards a full house, for example, you might put 3 jacks together next to a queen, hoping to gosh you could draw another queen somewhere along the line. Now, a combination is a smaller set of numbers, because you'll notice it's PNR divided by r factorial. Now, I strongly recommend that you take a little time to learn how to run a calculator. It does not take a monster to be able to do it. Most of the teaching that I do at Texas A&M, I carry this little Hewlett-Packard 32S calculator, which the last time I saw them, I don't know whether they make these anymore, cost about $32 at most stores. It has these things in it, so I can run PNRs in it. And one of my favorite things when I teach probability to the students is to point out to them that the probability of winning the Texas lottery is just about the same as the probability of getting hit by lightning. And we can calculate the probability of winning the Texas lottery if you assume, on the drawing of selecting of 6 numbers out of 50, that you're going to be the only winner out of there. It's about 1 in 17 million if you want to run it out. You can calculate all of these factorials by hand. And when you actually set it up, even if you calculate something like how many combinations are there of ways you can select 6 numbers from a population of 50, it turns out to be not quite so bad because there's a lot of canceling that you can do. Anyway, combinations and permutations. Remember the difference. Permutations, order is important. Combinations, order is not important. They cover only a few laws of probability. The first being the general character of probability, namely the likelihood that an event is going to occur. A probability always has a range of from 0 to 1. You don't have probabilities greater than 1 because that would be more than a certainty, and probabilities are not negative, contrary to popular opinion, especially if you've played too much poker. There are a couple of laws or properties of probability that are given. One is the law of total probability. And it says that the probability that event A or event B or both will occur is the probability that event A will occur plus the probability that event B will occur minus the probability that both A and B occur. Now, this is used a lot, and it's a very good one to watch for in the examples because you will find it frequently used. Incidentally, probability of this sort is highly used in the military, and some of you that have command responsibilities may have run into this when you try to figure out how many forces do you need to deploy in order to have a good probability of having achieved a particular objective. There is also the law of compound probability, or the joint probability, which is given here. If neither the probability of A nor the probability of B is 0, then the probability that A will occur given that B has is the probability of A given, I didn't say that quite right, given the joint probability of A and B. The probability is that the probability of A has occurred and then the probability that B has occurred given that A has taken place. And the converse is also true as shown over here. This one is a little less likely to be run into than the first one. This first one, for example, relates to the thing of why do you have 2 engines or more on commercial aircraft, hoping, of course, that the airplane will stay airborne on 1 or more engines. And the increase in reliability that you get by using 2 engines is given by this sort of probability up here. This material has probability functions in it, and particularly probability densities. It has probability distribution functions, and you will find that the binomial distribution sometimes crops up in these things. This CNX is the combination that we saw just a minute ago. The P is the probability it will occur. Q is 1 minus P. Normal distribution is beginning to show up in these exams, and it shows you the general form for this. And it points out that mu is the population mean, sigma is the standard deviation, and X is the event that you have in hand. And it gives you other information. I'm going to lay another one on you here because it also has the normal distribution tables. And it's not a bad table. You will notice that it has the f of x listed for you, the density, and it has the distribution function shown in here in several different ways, partial integrations of these things. If you integrate this from minus infinity to plus infinity, of course you get plus 1 under the curve, but it integrates from minus infinity up to a value x, and it also gives you the other half of it, the part of the curve that's remaining if you go from x out to plus infinity. It also gives you the ones from minus x to plus x, and the part that isn't there, shall we say, as well as the part that is. So it's got a lot of the information, and notice that these things are not given to you with really fine values of x. So consequently, if you're going to work problems that involve normal distribution on the fundamentals of engineering exam, you're going to be allowed rather wide latitude to interpolate between these two, and in fact, if you ended up with a number like 0.53, for example, they would allow you to grab a 0.5 Or if you ended up with a 0.58, you could pick up the 0.6. That makes problems a lot easier. In addition to the normal distribution, it also includes other distributions such as the t-distribution, but those are special cases of that, and I will pass over those in order to be able to cover more of this material. FE exams usually involve quite a bit of calculus. It gives you the basic definition for a derivative. It also shows you how to test for a maximum and how to test for a minimum as well as an inflection point. Now, let's look at that just a minute in case it requires any refreshing of your memory. If we have a curve which is coming along, and I'll show one with a maximum and a minimum, let's think about what's happening at this maximum. As we approach the maximum, the slope of the curve, which is the first derivative, is positive, but it's continually decreasing. When it crosses this point right here, the slope is horizontal, which means it's 0. And then it goes over the hill to this other side and it becomes negative. So we had a positive slope, which becomes 0, and which becomes negative. So if we were to plot the slope of the curve versus x over here, we'd have a positive value and we would be becoming negative. Right here where we cross the axis is the peak up here. But the slope of the slope, which is the second derivative, is negative. And that's pointed out for you here. Y is a maximum if its slope is 0 and its second derivative is negative. By similar token, if you sneak up on a minimum, you have coming over here a negative slope, then you become 0, and then you become positive over here. So consequently, if we look down here and see what's going on with the rate of change of the slope, it was negative, it becomes 0, and it goes positive. So when you're in a minimum, your second derivative is positive. Well, way to remember this, of course, is when you're at the bottom of the barrel, the only way is up, and your second derivative has just got to be positive. There's got to be a few things in life that are somewhat satisfying. An inflection point is a point where the second derivative is 0. Also, it's at a point where the second derivative changes sign as it goes through there. You can visualize an inflection point like this. It's kind of a point in an S curve. There are times when there are second partial derivatives calculated, and there is a definition of it here. Partial derivatives are, if you're not a mathematical devotee that does this all the time, partial derivatives can be a little daunting, but actually they're very easy. If it says, for example, take the partial derivative of something with respect to x, look at the something, differentiate every x that it has in it, and treat everything else as a constant, and you'll come out looking like a champ. It gives you the formula for the curvature of a curve, and it's a rather formidable looking thing. It's a second derivative divided by 1 plus y prime squared to the 3/2. It is used a lot. Dr. Lowry teaches courses in civil engineering for the deflections of beams, and EI y double prime is equal to the bending moment, and that y double prime is the simplification for the curvature. The radius of curvature is given here. Now, there is L'Hopital's rule. That is not La Hospital, that's L'Hopital. He's a Frenchman. L'Hopital's rule tells you how to find a limit when you have the ratio of two functions, and when you go to the value x equals a, for instance, as shown here on page 12, it shows you that if you get a 0 over a 0, or an infinity over an infinitive, you can still find the limit by differentiating the numerator, differentiating the denominator independently, taking the limit again. If it's still indeterminate, take the derivative again, and try the limit a third time. This time it may work. If it doesn't, differentiate again. If you get a finite value, that's the true limit. The manual defines integral and the fundamental theorem of integration for calculus, and fortunately, it gives you a very nice set of derivatives and of integrals. The couple of dozen derivatives and integrals that you have here are going to solve virtually every problem you're going to run into on the Fundamentals of Engineering exam. It's worthwhile reading this list to find out what kinds of things are here so you can be familiar with them. Integrals are used often to find areas, and this table shows mensuration of areas and volumes, so it gives you areas and volumes for typical shapes that we will normally run into in work on fundamentals of engineering. And there are 2 pages of them that are given to you. Lots of problems in engineering involve centroids and moments of inertia. This shows you how to find the centroid of an area. To refresh your memory, in case it's needed, if I have an area, and I'll show one up here like this, and I am trying to find the x-coordinate of that area, I can set up a differential element of area. This is the distance out to it of x. The area itself, this of course is dA, is equal to the integral of dA. The differential moment of that area about the y-axis is equal to, and this is the differential moment, x times dA, and the moment about the y-axis is the integral of that, okay? And the centroidal distance, x sub c, is equal to my divided by a, or it's equal to the integral of x dA divided by a. Okay? And that's the formula that's given to you. And also for mx, and there's a similar one for my. There is another term called a moment of inertia. Moments of inertia are used many different places. They occur in the bending of beams. They occur in the angular acceleration of bodies rotating about fixed axes. They are important in things such as gyroscopes, which may be used in your inertial navigation systems. They give the equations for these, and they give you the parallel axis theorem, which is very, very useful. Let me give you just a simple example of that. You might find it useful. Let me point out to you that if I have a rectangular area that's b units wide and it's h units high, the moment of inertia of this thing with respect to its centroidal axis, and everybody would recognize that the centroidal axis goes right through the middle, I is equal to bh cubed divided by 12. Sometimes people make up beams by putting various pieces together. So it might be necessary, for example, to get the moment of inertia of this rectangle with respect to this edge down here, which means you have to transfer it. And the distance you transfer it is h over 2. Now, I for this axis here, xc, is our bh cubed divided by 12, I sub xc. I sub x, which is parallel to that axis, but h over 2 units away, is going to be bh cubed divided by 12 plus the area, which is b times h, times the distance I transfer it squared, h over 2 quantity squared, and that's going to add up to bh cubed divided by 12 plus bh cubed divided by 4, and it's going to add up to bh cubed divided by 3. And that's just a simple example of how that formula is applied. Differential equations are very common on FE exams. The general form of the differential equation is shown here, and boy, they really pick a formidable way of describing it. Most of the differential equations that you will encounter in the FE exam will be second order. And a second order differential equation, the highest derivative is the second order derivative. And the differential equation, the ones they have here and the ones that we will find in the exams, therefore, are all linear differential equations, which makes life much more pleasant. Linear differential equations, particularly of second order, are of the form the second derivative of y with respect to x squared. There may be a constant out in front here. I'll call it, knowing what some of their notation is, I'm going to call it k2, plus k1 times dy by dx, plus k0 times y, equals, and there may be a function on the right-hand side. X is the independent variable. Y is the dependent variable. You tell me the value of x, and I will tell you the value of y. Y is dependent on what you tell me the value of x is. But this is the general form for these. For example, we might give you an equation that says that y double prime, the second derivative, plus 12y prime plus 100y is equal to 0. That's a second order linear differential equation. These equations have particularly easy characteristics for their solutions. Their solutions are the form of constants times exponentials raised to a power of a root times x. Let me explain that just a little bit. Y is equal to a constant, e, the natural number, to the rx. Now, actually, it's a sum of several of those. But the way we get the equation for the r is just to substitute this thing into the differential equation. Now, they show you here what that result is. And it is always going into the differential equation, where the order of the derivative is 2 there, you will get an r squared, plus the coefficient 12. The derivative of the equation there is order 1, and you will get a single r, plus 100 equals 0. Now in this equation, we have a quadratic result for r, and in this particular one, as I'll show you a little later, it comes out to be a complex conjugate, and we will see what some of those solutions look like. Actually, in second order equations, when you solve them, you can get any one of the 4 kinds of answers for quadratic equations. You can get 2 roots that are real and they are distinct. In other words, you can get a root such as -3 and -5. Both real roots, both distinct one from another. On the other hand, you may get two real roots, but they are repeated roots. The roots may be minus 3 and the repeat of it, another minus 3. On the other hand, there are roots to quadratic equations that are purely imaginary. For example, there is the equation r squared plus 100 equals 0, in which case r squared turns out to be minus 100, and r is plus or minus 10i, I being the square root of minus 1. In addition, you can get what are called complex conjugates. These are roots which have a real part plus an imaginary part. And the fact they are complex conjugates mean they will have a real part, such as minus 3, and an imaginary part, which might be 4i or minus 4i. In fact, the complex conjugates would be minus 3 plus 4i and minus 3 minus 4i. The complex part changes sign. It explains a lot about differential equations in a very few lines. It mentions right-hand sides, these f of x that I wrote down a minute ago, it calls it yp of x, in only 3 different forms: constants, exponentials, and trigonometric forms all by themselves. Those represent the 3 types of right-hand sides you can run into in these exams. It does a simple case of a first-order equation, and then it does the second-order equations. The first-order equation is very easy. They even give you the one with the 0 on the right-hand side. The second-order equations, they do all of the homogeneous ones for the 3 different types. And I am going to do 3 of them for you in pretty short order here so that you can see how they fit together. One of them will be the one that I did just a minute ago. Let me start off with this one. Y double prime plus 3y prime plus y, I want to make that 2y, equals 0. Okay? The equation for the characteristic roots is r squared plus 3r plus 2 equals 0. Now this is an easy one, and I chose it that way because I want you to see how it works. It factors into r plus 2 times r plus 1 equals 0. And it gives me the results r equal minus 1 and minus 2. The solution to the differential equation is y is equal to a constant c1 e to the minus 1x plus c2 e to the minus 2x. Okay? Let me give you another one. Let me change this differential equation a little bit and make it y double prime plus 6y prime plus 9y equals 0. The characteristic equation is r squared plus 6r plus 9 equals 0. And this factors into r plus 3 times r plus 3, and here equals 0. And we have to remember that r is equal to minus 3, or its repeat, minus 3. Our solution in this case is equal to c1 e to the minus 3x, but we don't want to write down another term which is just c2 e to the minus 3x, because that would be exactly the same as the first one. And what can be shown mathematically is that to be different, you throw in another x, c2x e to the minus 3x, and that always gives you another solution. Now, Let's take another one. This is called the differential equation for the simple harmonic oscillator. And it's y double prime, and I'll choose a particular value, 100y is equal to 0. Now in this particular case, the characteristic equation is r squared plus 100 equals 0, and we end up with r squared, of course, equal to minus 100, from which we conclude that r is equal to plus or minus 10i. Now, yes, that does give you a solution of the form y is equal to a constant, and I'm going to make him a script c1 e to the 10ix plus a script c2 e to the minus 10ix. It does give you that answer. But anybody who works with differential equations immediately jumps to the Euler formula, e to the I theta being cosine theta plus I sine theta, and changes this thing to a new form, c1, notice I've used a little different symbol, times the sine of 10x plus c2 times the cosine of 10x. Now you may look at that and say, well, that doggone prof at Texas A&M pulled a fast one on me because he had an imaginary term up here and it has disappeared in the next line. That's true. That's true. These constants right here turn out to be complex conjugates. These turn out to be real. And you will find if you substitute this back into the differential equation, it does satisfy it. Now, a minute ago, I had this other differential equation up here. Y double prime plus 12y prime plus 100y equals 0. And I had this form written down and this equation. We have to use the quadratic equation here in order to solve this. And we will end up with, thank you, we will end up with r equals minus b, minus 12, plus or minus the square root, b squared, 144, minus 4ac, so we're minus 400, all divided by 2a, a being 1 in this case. This is equal to minus 12 plus or minus the square root of 256 divided by 2. This is going to be equal to minus 12, that should be a minus 256, minus 12 plus or minus 16i, all divided by 2. Or finally, r is equal to minus 6 plus or minus 8i. Now, the solution, technically, is y equals e, let me use my script c1, to the minus 6 plus 8ix plus c2e to the minus 6 minus 8ix. And I can pull a term out of this of e to the minus 6x and write it, it's not going to fit on the page, well, maybe it will, times c1 e to the 8ix plus c2 e to the minus 8ix. Once I get to that point, then I can write that y is equal to e to the minus 6x times c1 cosine 8x plus c2 times the sine of 8x. And that solution is given in the manual. So you might review that one just to see how it works. The manual includes terms about Fourier series. Fourier series if you go to the University of Texas. But Fourier series are used in harmonic analysis. They give a form for it here, which is quite useful. They also show you how to calculate the Fourier coefficients, as shown here. There are occasional formulas that show, occasional problems that show up in sample exams. I have not seen them used extensively yet, but I would encourage you to review this one. Fourier transforms are shown here. These are getting a little on the advanced side. We do include Fourier transforms in the undergraduate courses which we teach here at the university, but they have not frequently shown up in things that I have seen in the fundamentals of engineering exam to this date. But the next one, Laplace transforms, surely have. Now Laplace transforms, as we commonly think of them, are defined in the equation shown right here. F of s is the integral from 0 to infinity, f of t e to the minus st dt. There is a way to calculate functions back out from Fourier transforms, but it's rarely used. So instead we use this series of tables. Now any of the Fourier transform, or excuse me, Laplace transform problems which you are given should come from this table here. And you can look through to see which ones there are. Difference equations are covered in this and are therefore free game. I have yet to see one on one of the exams, but that does not mean that they are might not appear, because it's quite possible that they would. Oh, there is another term that I have not yet seen on the exams, namely Z transforms, which are used in numerical analysis, but I have not seen one of those on the exam so far. Euler's approximation is a way of getting the next term of numerical analysis, and I encourage you to read that. It's straightforward. Numerical methods for getting the roots of equations, they give you Newton's method for extracting roots. And in the form that they quote it, it sure looks impressive, because I had to read that a couple of times. I thought I knew Newton's method, and I do. If you draw a graph and you think what we're trying to do when we're looking for a root occurs where a graph crosses the axis. And generally what we do, if we have no idea where the graph crosses, if it's not a second order curve where we can use the quadratic equation, and all you have at your disposal is a calculator, what you do is you go out and you guess a value, x naught, and you calculate the corresponding value on the curve. Well, it isn't 0. So what do? Well, if you know the equation of the curve, you get the slope of the curve. And you get the slope of the curve, and you can say, well, darn, if I could go out here a distance, some distance, I'll call it delta, I could get a better estimate for where I am, because then I could get over to here, go back, estimate it again, and I can sneak up on it, and all converge to where this thing crosses. And the way that that thing works is that if you have a guess, the nth guess, actually you have the nth x to the n minus 1, you have a guess and you want to make the next guess, you take the f of x n minus 1, divide it by the slope at that point, x of n minus 1, and subtract it off there, and that will get you where you're going. That sign there is necessary because of worrying about how the sign of the slope works here. So you get your next estimate by taking the one you've got, evaluate the function there, divide it by its derivative, at that point, change the algebraic sign, and add it to what you guessed before. It's what we call an iterative process. And it usually converges pretty fast unless you have a function that's got a lot of zero values closely packed together. And in that case, you can run into troubles with it. But you're not going to get those on the Fundamentals of Engineering exam. That covers the kinds of things that we have except for numerical integration. And the one that they give you for numerical integration that you're likely to use on the FE exam is Simpson's rule. And Simpson's rule is quoted for you here. It's a way of calculating the area under a curve where you have equally spaced data, for instance, and you have an even number of intervals, and you pass parabolas through those to connect the points. It does a very good job under most circumstances. It also covers just a tiny bit about the numerical solution of differential equations. Frankly, for the numbers of problems they're giving on the FE exam at this time, I can't imagine how you would derive a problem for the numerical solution of differential equations. It could be worked in either 2 minutes or 4 minutes, which is about the amount of time you have in either the morning or the afternoon session. That gives you an overview of what's in this manual. And I encourage you to read this. This is what the cover sheet looks like. Oops, that's not the cover sheet either. So I've got it buried somewhere here. The cover sheet is where? That's the advantage of having such a large number of sheets of paper. Here we go. There's the cover sheet. Fundamentals of Engineering, Discipline-Specific Reference Handbook, and it has the kinds of information you're going to need. In just a moment, we'll start in on problems. I'm on camera. Are we on now? Hello again. Having given you a lot of the information about what's going on with respect to the manual that you get to take into the examination itself, at this stage we're going to look at problems, actual problems that have been used on examinations, and there have been a variety of these put out. The ones I'm going to use first were published by the National Council for Engineering Examiners, and it's the Fundamentals of Engineering sample questions. In particular, it's the sample questions related specifically to mathematics. Now, of course, the problems that were taken from areas in statics, dynamics, electric circuits, and all the other areas will involve mathematics as well. But these problems are specific ones in mathematics for the sake of mathematics. But they are nonetheless indicative of the kinds of problems which engineers encounter. This page shows you what the exam actually looks like. For example, remember I told you that some of the problems involve partial derivatives? And if you're paranoid about partial derivatives, think of the lucky people who took this exam and the first problem they run into is a partial derivative. Given the function, compute the partial derivative of y with respect to x. Given you choice A, choice B, choice C, or choice D. The next one gives you a problem in probability and statistics. The next one gives you a function defined in terms of a determinant. The next one asks you to, the first derivative of function is the one given above, to ask you to calculate the first derivative of it. Finally, we have one that involves a Laplace transform, the Laplace transform of a step function. Well, we've seen what the beast looks like. Let's take a look and find out what some of the solutions are like. I've written this out in bigger form, and I've stated the problem more succinctly so that you can see more readily what is going on. The function y is x squared z plus 3z squared x plus 6 times the quantity x plus z, and you're asked to differentiate it, take the partial derivative if you will, with respect to x. When you perform that partial derivative, you'd regard z as a constant, just as you would regard 3 or 6 as constants. So the partial of y with respect to x is 2x times z plus 3z squared times x, because the x gets differentiated out, plus 6. And when you look down the list, you find out, lo and behold, there is one there, and it happened to be answer A. Now, here's a nice probability problem for you. Balls are numbered 1 to 100. They are drawn. One is drawn. Determine the probability that the number is odd or greater than 100. Well, think about that for a minute. There are two things going on. There are odd balls in there, 50 of them to be exact, out of the 100. So the probability that you're going to pick a ball out and it is odd is 50%, or a half. On the other hand, there are 20 balls in there that are greater than 80. There's 81, 82, 83, on up through 100. So there are 20 of those folks in there. Some of them are odd, like 81, 83, 85, 87, 89, and so forth. So there really are only 10 additional candidates that you run into out of that category. Now, the probability that it is odd and greater than 80, the probability is greater than 80 is 20. The probability that's odd and greater than 80 is 10 in 100. So using the probability formula as given in the manual, the probability that's odd or greater than 80 is the probability that it's odd plus the probability that's greater than 80 minus the probability that it is both odd and greater than 80. And you will notice that you come out with 50 plus 20 minus 10, and it's equal to 60 over 100. So the probability is 0.6. So you got a better than even chance, as you would expect that you should have from a problem like that one. Okay? Now, let's take a look at that next one that involved that determinant. That seemed like kind of double jeopardy, you know. Here you're given an f of x, and the darn thing, you've got a 2 by 2 determinant, x, x squared, x cubed, x4, and so forth, and you're supposed to determine the first derivative. Well, the easiest thing to do is to first of all figure out what is the function of x. Multiplying this diagonal, we get x to the 4, so we get x times x cubed, that's a plus. Coming back against the grain, we get a minus, x squared times x to the 4th, that's minus x to the 6th. We take the first derivative of it, we're going to get 4 x to the 3rd power minus, from this minus sign right here, 6 x to the 5th power. Okay, and there is such an answer. Now, the next one asks you to determine the Laplace transform of the unit step function of magnitude A. For those of you in the audience that are an electrical engineer, this is duck soup. Electrical engineers are very fond of unit step functions. Now, mechanicals like them pretty well too. But the unit step function looks like this. If you plot a function of f of t going along here, it comes along here at 1 and actually jumps up to a value of a and then continues indefinitely at that value from here on out. Now, if you're really an eager beaver, you can stuff this thing into the integral and you can calculate it out as I have done here, and you can find out that it's equal indeed to a divided by s. However, you can also look at the table on page 17 in column 2 and you will find that the Laplace transform of the unit step function is just 1 over s, and the Laplace transform of one which is of magnitude a is just a over s. And that is listed as answer B. So that is an easy one. It's always nice when you're taking these exams to kind of run through them to begin to get an idea which problems are truly easy ones. Because there are a few of them like this that are very easy, and you can knock them off in an incredibly short period of time and gain yourself ground for working one that is harder. Now, some of them are more difficult than others. Some of them just simply require that you have to read it fairly carefully. For example, in this one it says what they want is the estimate of the mean M of a population by drawing a sample size N and calculating its mean. You folks are at Fort Hood. You get a shipment of armament, and you want to check out to find out whether the shells for a particular tank have been manufactured properly. So you've got